Hello and welcome to the first video on chapter 3, which is about derivatives. This video covers the first sections 3.1 and 3.2. Objectives. These are objectives for the first two sections of chapter 3. First, find the derivative of a function using the limit of the difference quotient. Then find the derivative of a function from its equation. Then find the tangent and the derivative at a point. Recognize the derivative as a function. Recognize the relationship between continuity and differentiability. And identify the points where a function is not differentiable. Introduction to derivatives. Let's start with a function f of x with a single term. If we take the term f of x equal to 0, then 0 cannot be the base of an exponent. There is no exponent that's called 0 to the power 5 or 0 to the power 6. So that's not going to work. So df by dx is not going to work for f of x equal to 0. Let's take a look at f of x equal to constant. When f of x equal to constant, that means the graph of the constant is a straight line that's parallel to the x-axis. If it is parallel to the x-axis, then its slope is equal to 0. So if we get the derivative of a function that has a slope 0, it's going to be equal to 0. So because c is a constant. So that's not of too much interest for us. What is of interest for us is the next one. Let f of x equal to a multiplied by x to the power k. Now we're talking business, because if x changes, then this term will change. And that's what is known as a function and dependent variable and independent variable. The dependent variable is x and the independent variable is the right hand side, which is f of x. Now let f of x be equal to a x to the power k be the function where a is a constant. The derivative of f of x is symbolized as d by dx of a multiplied by x to the power k, and this is equal to ak, and then obviously we have the k there, a to the power k, so the power k will be taken down as a coefficient along with a, and a new coefficient is determined, which is k minus 1. So that is how the derivative is. We take k, we mount it down next to the a, so it will be k multiplied by a, and together there will be the new coefficient, and the new exponent will be k minus 1. So we can say as conclusion, derivative d by dx of a sub n, which is a coefficient, a constant, x to the power n plus b is a constant, is equal to n, we take n down along with a sub n, so the new coefficient will be n a sub n multiplied by x to the power n minus 1. And then derivative of b is equal to 0, because we said derivative of constant is equal to 0. So this is the general formula for any derivative. Any derivative, we proceed with it this way. Let's take a look at more. Derivative of a polynomial. A polynomial has the form, the general form for the equation of the polynomial f of x is given by the following. F of x equals to a sub n x to the power n plus a sub n minus 1 x to the power n minus 1 all the way until a sub 1 x to the power 1 plus a sub 0 x to the power 0. This is a constant value since x to the power 0 equal to 1. The rest are functions of x. So the derivative of f of x denoted by df of x by dx is as follows. We have to get d by dx, and then we have all the terms. We're going to fill them gradually. So these are the terms. Now if we want to do the derivative will go as follows. Just watch the computer. The n is going to move and come down here, and it will be replaced by n minus 1. Now it will be replaced by n minus 1. And over here also, the n minus 1 is going to move down over here, and it will be replaced by n minus 2. Replaced by n minus 2. And of course, this term x to the power 1, if we did the derivative, the 1 will be coming and will be multiplied by a1, so it's not going to have any impact, and x to the power 0 becomes a 1. So we will be left with a1 only. And this term is constant, so derivative of constant is equal to 0. So this is what we'll end up having. So this is the derivative of the polynomial. Okay, let's take a look at the conclusions from what we went through. Number 1, derivative of f of x, which is a polynomial, we can do it d by dx of all the terms between parentheses or between curly brackets. The derivative will be the derivative of each term separately, d by dx of the first term plus d by dx of the second term, all the way until d by dx of the last term. That is conclusion number 1. Conclusion number 2 is the fact that d by dx of the general term a k x to the power k equal to a derivative of x to the power k. Why? Because a is a constant. So the derivative of a constant times the variable, we take the constant out, will be just the constant out and then the derivative of the variable. The third thing that we learned from this is d by dx of a1 x to the power 1. When x is to the power 1, d by dx of a times x to the power 1 will give us a, and x to the power 1 will disappear because it will be x to the power 0 equal to 1. The last conclusion is d by dx of the constant is equal to 0. We're going to go ahead and start section 1 in chapter 3. It's about tangents and the derivative of a point. By the way, the derivative of a point is something that you cannot do it using numerical methods or differential equations or linear algebra or any science, any mathematical science, or for that matter any science. This is the only area that only calculus can provide, and this particular point is half of the calculus. We'll talk about this half and we'll talk about the other half later on. So let's enjoy this half. We're going to go ahead and look at the slope of the curve. We already know the idea. We had an idea about how to calculate the slope of a tangent line at a given point from chapter 2. The idea was to approach the slope of the tangent line using the secant lines. Now we formalize this idea as follows. The slope of the curve y equal to f of x at a point p of x naught comma f of x naught is the number m, where m is given by limit as h goes to 0 f of x naught plus h minus f of x naught divided by h, assuming that the limit exists. The tangent line to the curve P is a line through P with this slope, that is the slope m. And this figure we went through it several times, so I'm not going to waste your time on it. You could just go back and review it if you want to later on. Example 1. Find the slope of the curve y equal to 1 over x at any point x equal to a, but a should not be equal to 0. What is the slope at the point x equal to -1? Let's deal with the first question first. So y equal to 1 over x, y prime means the derivative d by dx of 1 over x equals to d by dx of x to the power -1, and that will give us the answer is negative x to the power -2, and that's equal to -1 over x squared. The slope at x equal to a, we just plug in a instead of x and we'll get the slope -1 over a squared. The second part of the question, what is the slope at the point x equal to -1? We just replace the slope here. The slope here in x squared, we replace it by -1 square. So -1 square will give us +1. So -1 over +1 is equal to -1. So the answer to this, what is the slope at the point x equal to -1? Equal to -1. Second question, where does the slope equal to -1 over 4? So the question is where. So since the slope is equal to -1 over x squared, then -1 over x squared equal to -1 over 4, then we can tell that x squared must be equal to 4. So therefore x squared equal to 4. The slope equal to -1 over 4 when x is equal to plus or minus 2. Why? Because x squared equal to 4, that means x will be equal to plus or minus 2. The third part, what happens to the tangent to the curve at the point a comma 1 over a as a changes? The tangent at a comma 1 over a will change since it equals to 1 over a square. If you change a, it's going to change the tangent. However, it will not change under one condition. If you change x to be y and y to be x. If you put 1 over a as the x coordinate and a as the y coordinate, then it will not change if a changes. That's it. Let's take a look at more examples. This figure provides a solution to the points that we just discussed. This figure is about the tangent slopes steep near the origin become more gradual as the point of tangency moves away. You can go from the top in y equal to 1 over x. It's going to be very steep here, but then it's going to start to become gradual, the slope. What you see here is the slope at the point A is 1 over a square, as we just finished the exercise in the previous slide. Also, if this point is -1 for x, then the slope will also be -1, as we mentioned in the previous slide when we solved the exercises. This figure pretty much shows the answers that we went through. Basically, this is the curve for y equal to 1 over x, and this is the other image of it because it is an odd function. So this is just like an image of it if we assume this as an object. Now, one of the questions was find out the values of x for which the slope is -1 over 4, and we solved that problem and we found out x could be either -2 or +2. And obviously over here this is -2, and for -2x you put -2 over here, y will be equal to -half. And for +2 you put +2 here, y will be equal to half. So these are the x coordinate, y coordinate, x coordinate, y coordinate. So also if you look at the curve, the slope will be gradual, but nearing the origin will be very steep, and then after that will continue gradual on this direction and on the other direction. So the two tangent lines to y equal to 1 over x having slope -1 over 4, as we mentioned before. The following definition is just like a review for you. It's about the derivative of a function f at a point x0, denoted by f prime of x0, is f prime of x0 equals to limit as h go to 0 of f of x0 plus h minus f of x0 divided by h. The following are all the interpretations for the limit of the difference quotient, which is this one. Number one, the slope of the graph y equal to f of x at x equal to x naught. Number two, the slope of the tangent to the curve y equal to f of x at x equal to x naught. Number three, the rate of change of f of x with respect to x at x equal to x0. And the last one is the derivative of f prime of x naught at a point. All these apply. That's it, at least for now, for derivatives of points. Now we're moving to section 2 on chapter 3, and this is about derivatives as a function. Definition: the derivative of the function f of x with respect to the variable x is the function f prime whose value at x is f prime of x equals to limit as h goes to 0 of f of x plus h minus f of x divided by h, provided the limit exists. Alternative formula for the derivative is the following: f prime of x equals to limit as z goes to x of f of z minus f of x divided by z minus x. The way to prove this is just take h equals to z minus x and the rest will be history. You could figure out the rest, but these two are identical. Example number 1. Differentiate f of x equal to x over x minus 1. We use a definition, so d by dx of f of x equal to limit as h goes to 0, x plus h divided by x plus h minus 1 minus x divided by x minus 1 all divided by h, and this is equal to limit as h goes to 0, x minus 1 multiplied by x plus h minus x multiplied by x plus h minus 1. If we do the math and multiply these two and subtract from them the multiplication of these two, we get this line. Limit as h goes to 0, x squared plus xh minus x minus h minus x squared minus xh plus x divided by h multiplied by x plus h minus 1 multiplied by x minus 1. Now we can observe that there is x squared and minus x squared. There is xh and minus xh. There is x minus x. So all of this will be gone. So let's go ahead and cross out x squared with x squared and x with x and xh with xh. The only thing we'll be left with is h in the numerator, but also we have h in the denominator. So these two h's will cancel each other and we will get this equation. Limit as h goes to 0, negative 1 over x plus h minus 1 multiplied by x minus 1. And if we execute the limit, then this h will be equal to 0, and that's what we have over here. And once we put this to 0, then the result will be negative 1 divided by x minus 1 all squared, and that is the derivative. Example 2. Find the derivative of f of x equal to square root of x for x greater than 0. First, we will do the first part first, and then we'll get back to the second part. So solution for the first part, part A, limit as x goes to 0, f of x plus h minus f of x divided by h equals to limit as h goes to 0, square root of x plus h minus square root of x divided by h. This is equal to limit h goes to 0, square root of x plus h minus square root of x divided by h. Now we will multiply the numerator by square root of x plus h plus square root of x, and multiply the denominator by the same value, square root of x plus h plus square root of x. If we do the math, multiplying this numerator by this numerator, we'll end up with x plus h minus x. And if we multiply the denominator by the denominator, we'll get h multiplied by square root of x plus h plus square root of x. Now we realize that we have x, and negative x or minus x. So we can cancel x with x, and we will have only h on the top. But also we have h in the bottom. So if we cancel the x's, then we will have h on the top and h in the bottom. So let's suppose that we cancel these two. We will end up with 1 in the numerator, which is right here, and the denominator will not have h anymore. It will have just the square root of x plus h plus square root of x. If we execute the limit, then this h will be equal to 0. So we'll end up having 1 over square root of x plus 0 plus square root of x, which will lead us to 1 over 2 square root of x. That is the derivative of f of x equal to square root of x. The second part says find the tangent line to the curve y equal to square root of x at x equal to 4. The slope of the tangent equals to, since this is the equation for the slope and we're given x equal to 4, we plug in 4 here, and that's what we'll get. 1 over 2 square root of 4, which is going to be equal to 1 over 4. Therefore, the tangent is the line with slope equals to 1 over 4. Now we have a few notations to bring it to your attention. There are many ways to denote the derivative of a function y equal to f of x, where the independent variable x and the dependent variable is y. Some common alternative notations for the derivatives are f prime of x, y prime, dy by dx, df by dx, df of x by dx, capital D of f of x, capital D with subscript x of f of x. These are just notations that you may find if you're trying to look at different resources in the internet or some books. You will find different ways of representing the derivative. So that's all okay. Now, example 4. Show that the function y equal to the absolute value of x is differentiable on the interval from negative infinity to 0, not including 0 or negative infinity, and from 0 to positive infinity, not including 0 and positive infinity. Now, but has no derivative at x equals 0. So we want to show that it has no derivative at x equal to 0. And we can show that it has no derivative at x equal to 0 if we can prove that x equal to 0 is either a cusp or a corner or a vertical tangent or a jump. So we have to find out one of these to prove that there is no derivative at x equal to 0. So y equal to mod x in general implies that y equal to x for x greater than 0 and negative x for x less than 0. Therefore, let's go ahead and take the derivative of the mod x of y. So we take the derivative by taking the limit as h goes to 0 of mod x. And this equals to two possibilities. Limit as h goes to 0 of x plus h minus x over h for x greater than 0. And it's equal to limit as h goes to 0 of negative x minus h plus x over h for x less than 0. Now, if we do the math and apply the limit, we can see that x goes with x and I have h over h. So h over h is equal to 1 over 1. So the limit will not make any difference because we have 1 in the numerator and 1 in the denominator. So we have 1, and over here in the bottom we have negative 1 because the x goes with the x and the h goes with the h, but we have negative h, so it will be negative 1. So the answer is negative 1 for x less than 0. So we have positive 1 for x greater than 0 all the way until infinity. And we have negative 1 for x less than 0 all the way until negative infinity. And this is pretty much like the graph of the derivative. So we can see that it is greater than 0 equal to 1 for x greater than 0, not including 0. So there is a dot that's open, and not including also 0 when it is going towards negative infinity. And the graph of f prime of x shows a jump at x equals 0. And there is a jump right there because 0 is not included anywhere. So the graph is not differentiable at 0 because there is a jump. Hence, mod x is differentiable at everywhere for the set of real numbers except for 0, and that's why we're excluding 0 here. So 0 is not included on the left side and 0 is not included on the right side because we have the parenthesis. Parenthesis means not including 0 on both sides. That's it for this one. We will now go ahead and look at example 5. In example 2, we found that for x greater than 0, the derivative d by dx of square root of x equal to 1 over 2 square root of x. We apply the definition to examine if the derivative exists at x equals 0. To do so, let's start with f prime of 0 equals the limit as h goes to 0 of f of 0 plus h minus f of 0 divided by h. This is equal to limit as h go to 0, f of h minus f of 0 divided by h. And this is equal to limit as h goes to 0, the square root of h minus the square root of 0 divided by h. And this is equal to the square root of 0 minus the square root of 0 divided by 0. However, the derivative does not exist because we have 0 divided by 0, and that's not defined. So the derivative does not exist. It's also clear from the formula d by dx of square root of x equal to 1 over 2 square root of x. If we plugged in d by dx of square root of 0, it will be equal to 1 over 2 multiplied by the square root of 0, which will give us 1 over 0, which is equal to infinity, which also leads to the same fact. Now we're going to take a look at two examples where the derivative does not exist. Number one, a corner. If you look at the corner, the corner is right here. It is sharp. This is a straight line and this is a curve. So this is a corner. If we look at the tangent that passes through P, you can see this purple line. This is one tangent. It's passing through P. Also, you see this purple line on this side. This is also a tangent that's passing through P. So which one should we use? The derivative must be equal a unique value, but they have two examples of tangents, so two different slopes. Which one is equal to the slope for the derivative? Anytime that we have more than one slope at the same point of a curve, then we can say that the derivative does not exist on a corner. Likewise, a cusp. A cusp is just like the corner. A cusp where the slope of PQ approaches infinity. Why? Because if a cusp is like this, and then we choose to have the line that passes through this point as tangent to the curve, that point this line will have infinity as it is tangent. So the cusp where the slope of PQ approaches infinity from one side and negative infinity from the other side, this is not differentiable at P. Also, we can define a vertical tangent. A vertical tangent, if you see this curve, it's going this way and then it's changing direction. So at the point where it's changing direction, you can draw a vertical tangent. If you draw this vertical line, vertical lines do not have a slope. Their slope does not exist. Since the slope does not exist, then it's not differentiable there. Also, we have discontinuity. We can see that we have this curve is discontinued at this point, the open dot, and of course we have the closed dot over here. So since we have discontinuity, then the function will not be differentiable at the discontinuity. And this is another example. Okay, this is another example. We have discontinuity in the middle. So the function is differentiable everywhere except when the point is not in the domain. This point is not in the domain, so there is no way that you can differentiate a point that's not in the domain. Now we will go through the theorem of differentiability, and this theorem states differentiability implies continuity. If f has a derivative at x equals c, then f is continuous at x equals c. And this is clearly very necessary and important. Let's go ahead and take a look at the examples that we just went through. One example is for like the corner, and the other example is for like the cusp. And the other examples we had like discontinuity, discontinuous functions, and also we had the vertical tangent. So if we have a tangent over here at this point P, so all of these points we are not differentiable. And if let's call this one P is not differentiable here because vertical tangent has infinity as it is tangent, and that doesn't work. The cusp, we explain the reason, and for the corner we explain the reason, and also for the discontinuity. The function is discontinuous, so it's not differentiable. If it is differentiable, then it's continuous. Now what's the difference between these two? Let's say this two, this one and this one. Okay, this one is differentiable because this point is a closed dot. This one is not differentiable because this is an open dot. This is not differentiable, and this is differentiable. So if it is differentiable, it's continuous. Now it's continuous, but this one is not differentiable, so it's not continuous at this point. So we can say if a function is differentiable, then it's continuous. Differentiability implies continuity. Okay, but continuity does not imply differentiability. Why continuity does not imply differentiability? This function is continuous, but it's not differentiable. This function is continuous, but not differentiable. This function is continuous. If you draw it, you can draw it without taking the pen. It's continuous. It's continuous. This is continuous. This is continuous. This is continuous. The only one that's not continuous is this one. This is not continuous and not differentiable. Every one of these three continuous, 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 but not differentiable. So every function that's differentiable is continuous, but not every continuous function is differentiable.